section 1.2, Applications and Modeling with Linear Equations, we're going to look at solving all sorts of different types of problems, including geometry, interest problems, mixture problems, uniform motion, and work problems. Now, there are some general strategies that you can use to help you solve these problems, and they are listed here. Number one, draw a picture, graph, etc. to help you solve the problem. Number two, assign variables and verbal descriptions of what the variable represents. 3, write the equation that models the given situation. Use the variables that you declared above. 4, solve the equation. And then 5, interpret your solution and check for the reasonableness of your solution. Now, honestly, these steps 1 through 3, you sort of do those in conjunction. You're thinking about what picture to draw or what table to create. You're thinking about what variable to use in the table or what variable to assign to some part of the geometric picture, and then you write out the equations and use those variables. So you're sort of thinking about all these at the same time. Just make sure you accomplish all of those before you solve the equation. Let's look at an example from geometry. Example 1. A building is in the shape of a rectangle. It's 100 feet by 200 feet. A sidewalk of width x feet will be added around the building on all sides. If the new perimeter around the sidewalk and building together is 664 feet, what is the width of the sidewalk? So here, because it's a geometry question, we'll definitely want to draw some sort of picture. I'm going to start with the building itself. And it's a rough sketch, but we know the building is 100 feet by 200 feet. And then next, on all sides, we're going to have x feet of sidewalk. So I'm going to draw it. It may not be to scale. That's okay. It's going to go out like this. So that's x, and that's x, and down here, another x, another x. It's x all the way around, and even in the corners here. So we have it, and it looks like this. Alright, so that's the picture. Maybe I'll call that number 1. Number 2 was to assign variables. So we're going to have length, I'll call that L, and width, W. And the length, we'll use that as the longer side going up and down here. So we start with the building itself, and that's 200. But then we're going to add x feet of sidewalk on the top side here, and x feet of sidewalk on the bottom side. So that's going to be 200 plus 2x. And we do the same thing for the width. We'll start with the building itself. That's 100. Plus, on the left side, I have x extra feet of sidewalk. And on the right side, I have x extra feet of sidewalk. So this is 100 plus 2x. And then 3, what geometric aspect have we been thinking about? We've been thinking about the perimeter. The perimeter of a rectangle is P is equal to 2 times the length plus 2 times the width. Step 4, we'll create the equation to solve. So the perimeter that we know we're going to end up with is 664 feet. That's equal to 2 times L. L is 200 plus 2x from step 2, plus 2 times the width. Well, the width is 100 plus 2x from step 2 as well. And now we have our equation that we can solve. We'll solve for x, and that'll tell us the width of the sidewalk. So solving this equation of 664, I'm going to distribute the 2 on the right side. So that's 2 times 200 is 400, plus 2 times 2x is 4x. Same thing on this second term. 2 times 100 is 200, and then 2 times 2x is 4x. On the right side, I'll group together the constants. 400 plus 200 is 600. And we also group together the x's. 4x plus 4x is 8x. Move the 600 to the left side and subtract. That leaves me with 64 is equal to 8x. Divide both sides by 8, and we get x is equal to 8. And then step 5, interpret the reasonableness. Yeah, that's reasonable. So the sidewalk is 8 feet wide. Let's look at example 2 on the next page. We have a simple interest question. Leslie invested a total of $3,000. Some of the money was invested in Fund A, which earned 4% simple annual interest for 3 years. The rest of the money was invested in Fund B, which earned 6% simple annual interest for 4 years. In total, she earned $576 in interest. How much was invested in the account? All right. This is a great problem to draw a table. And we're going to have several parts to our table. First one is we're going to have things that happened with Fund A and things that happened with Fund B. And what we want to look at first off is the amount invested in each of the funds. Then we'll apply the interest rate to figure out how much money there was earned in interest. And to do that, we also need the time. Now you should be thinking about what equation to use, and that would give us a hint about what the pieces of the table should be. I'll go ahead and tell you in step 3, the interest formula for simple annual interest, and this is one that you should know for the test, is interest is equal to principal, that's the amount invested, times the rate, R, written as a decimal, times the amount of time it was invested. So I is equal to PRT. Now, we need to fill in the parts of the table that we know. We know that Fund A had an interest rate of 4%. I have to write that as a decimal, so that's 0.04. And the money was invested in Fund A for 3 years. For Fund B, the money earned 6% interest. That's 0.06. And that was invested for 4 years as well. Now the question is, how much was invested in each account? And we don't know, and that's what we're looking for. So I'm just going to go ahead and declare that X is the amount that was invested in Fund A. And I'll put that down here in my variable declarations as well. X is equal to amount invested in Fund A. If we invest $3,000 total, and I've already invested X amount in Fund A, then the question is, how much is left for Fund B? Well, if I need 3,000 total, it must be 3,000 minus X. It's the amount that's left over after I invest X in Fund A. Now the table is complete, and we have the 3 elements. We have the principal, the rate, and the time. And then Fund A is going to earn a certain amount of interest, and then Fund B is going to earn a certain amount of interest as well. Let's go ahead and calculate those now. So from Fund A, I'm going to call that I sub A to represent the interest earned in Fund A. It would be the principal, X, times the interest rate, 0.04, times the time, 3. And those are just the elements from the table in row Fund A. We multiply these together, and we get 0.12x. I'll do the same for Fund B. The principal is 3,000 minus x. The interest rate is 0.06, and the time is 4 years. If we multiply these together, you end up with 720 minus 0.24x. And now we know that the total interest is equal to the interest earned in Part A, Fund A, and the interest earned in Fund B. The total interest was $576. So now we substitute everything that we know. 576 is equal to 0.12x from previous calculation, plus 720 minus 0.24x. We're going to move the 720 from the right to the left. If I subtract 576 minus 720, I get negative 144. And on the right side, if I subtract 0.12x minus 0.24x, I get negative 0.12x. And then to solve for x, I'm going to divide both sides by negative 0.12. And so we get x is equal to 1,200. Now looking back at the table, x was the amount invested in Fund A. So $1,200 was invested in Fund A. And I need to do a calculation to figure out how much was invested in Fund B. We know that Fund B was, the amount invested was 3,000 minus x. So this is 3,000 minus the 1,200, which is 1,800. And so there we have $1,800 was invested in Fund B. Let's look at example 3. A chemist has both 2% hydrochloric acid solution and 1.2% hydrochloric acid solution. How much 2% solution should be mixed with 10 liters of 1.2% solution to make a solution that is 1.75% hydrochloric acid? Again, this is a great problem to create the table. So we're going to have solution 1. And solution 2. And then we're going to have the mix. Now, the amounts of solution that we're going to use, along with their concentration, if I multiply the amount of solution times the concentration of that solution, that'll tell me how much of the actual chemical I have. In this case, it's the amount of hydrochloric acid. So we know that we have a 2% solution for the first one, so that's 0.02, and a 1.2% solution for the second one, so that's 0.012. The mixture needs to be 0.0175. Now we need to be thinking about the formula, and I've somewhat given it to you already. It's the amount times the concentration, that is equal to the amount of chemical, in this case hydrochloric acid. So we don't know how much of the 2% solution is used, so I'm going to call that X and declare that here. X is equal to amount of 2% hydrochloric acid solution used. And put this down as the units, liters. We know how much 1.2% solution was used. That was 10 liters. So you're going to have a bottle of 2% solution, another bottle of 1.2% solution. You're going to take some and mix it into a bigger bottle, and together you're going to have X plus 10 liters of the mixture. Now, because you're using a different amount of the concentrations, you're going to end up with a different concentration that's somewhere between 2% and 1.2%. In this case, 1.75%. So let's multiply this across. I'll multiply here. So the amount of hydrochloric solution from solution 1 is 0.02x, and from solution 2, it's 10 times 0.012. And then overall, the mixture should work the same way. The amount times the concentration. I'll write it this way maybe. 0.0175 times x plus 10. And then what we know is that the hydrochloric acid part from the first solution added to the second solution should be equal to the amount in the total mixture. So we're going to add the elements from that last column. So 0.02x plus 10 times 0.012 is equal to 0.0175 times x plus 10. Now let's simplify. So 0.02x plus 0.12 is equal to 0.0175x plus 0.175. I'm going to move the 0.0175x from the right side to the left. When I do that, I subtract it from 0.02x. This is going to be 0.0025x. Next, I take the 0.12 from the left, move it to the right, and subtract, and I get 0.055. Finally, divide by the coefficient, 0.0025, and we get x is equal to 22. So step 5 is 22 liters of 2% hydrochloric acid was used. Next, let's look at uniform motion. The key formula in uniform motion is distance is equal to rate times time. In example 4, we have Carl was biking to work one morning, a total distance of 5 miles. Along the way, the bike got a flat tire and Carl finished the trip on foot to work on foot. Carl can bike 10 miles per hour faster than he can walk. If he spent 20 minutes on the bike and 12 minutes on foot, how fast was he going on the bicycle? Again, that's a good problem for a table. So let's create a table. We're going to have the bike. and on foot. And distance is equal to rate times time, so we'll have the rate, the time, and the distance. We're looking for how fast he was going on the bicycle. And we know that he can bike 10 miles per hour faster than he can walk. So there's two ways to set this up. I'm going to set it up the following way. I'm going to say that x is equal to his speed on foot. And put the x under rate and foot. Now, knowing that he can bike 10 miles per hour faster than he can walk, that means that his rate when he's bicycling is x plus 10. Now I'm going to include the units on both of these so that you can see what has to happen here. And I'm going to write it a little strangely. I'm going to write it as miles divided by hours. That's literally what miles per hour means. Anytime you have a rate, you end up with this division type unit, something over something else. Usually, in this case, it's a distance divided by a time. And that comes straight from the formula above. What that tells me is that the elements that go in the time column have to be in the form of hours in order to get hours to cancel. Because we're going to multiply across. Rate times time is equal to distance, so I need the hours to cancel. It says that he spent 20 minutes on a bike. Well, that's in the form of minutes, so I need to change that. I know that there are 60 minutes in an hour, so 20 minutes is actually 20 over 60 hours, and I'll go ahead and simplify that while we're here. 20 over 60 is 1/3 of an hour, certainly, and the amount of time on foot was 12 minutes. I need to change that to hours as well. 12 divided by 60 is 1/5 of an hour. And now we multiply across to get the distances. So we're going to have the rate of x plus 10 times the amount of time, it's 1/3, and we'll have the rate of x times 1/5. Now together, Carl spent time biking and then walking on foot. So the distance that he biked plus the distance that he walked is going to equal the total distance, which was 5 miles. So let's set up the equation. I'll go ahead and fill in the rest of this that we used along the way. The equation was, the variable was x as the speed on foot, and the equation we used, of course, was distance equals rate times time. So let's set this up. So 5 miles total is going to be equal to the distance on the bike plus the distance on foot. And just pulling in these elements from the chart, the distance on the bike was x plus 10 times 1/3 plus the distance on foot was x times 1/5. We have an equation that has a fraction, so let's compute the LCD. We have a 3 and a 5, and so the LCD is 15. So I'm going to multiply both sides by 15 and cancel denominators. So we have 15 times 5, and then 15 times x plus 10 times 1/3 plus 15 times x times 1/5. I also distributed in that step. So we have 75. On the right side, 15 divided by 3 is 5. So we have 5 times x plus 10. And on the right side, second term, 15 divided by 5 is 3. We have 3x. Distribute the 5 in the middle here. So we have 5x plus 50 combine the x's on the right side. We have 75 is equal to 8x plus 50. Move the 50 over. We get 25 is equal to 8x. Divide both sides by 8. So the answer is 25 over 8. Since this is a word problem, I'll go ahead and write a decimal. And that's 3.125. Now, what does x represent? X represents a speed, so it's miles per hour. But this is the one that we declared was on foot. Now, this is where it comes in handy to give a very sharp visual, verbal description of your variables. X is the speed on foot. The question clearly asks for how fast was he going on the bicycle. So we now use X and the table to figure out what his speed on the bicycle was. That would be X plus 10. So we take our result and we add 10. So it's 3.125 plus 10, which is 13125. Don't forget your units, miles per hour. Example 5, Bob can wash a car in 10 minutes. Carl can wash a car in 12 minutes. Question A, how long will it take them working together to wash 3 cars? Well, I don't really see a picture I can draw here, or a table, so I'm going to go on to number 2, and that's declare the variables. So T is going to be equal to the time washing cars together. And then we're going to have 2 different rates, so I'm going to use subscripts here. R sub B is going to be the rate Bob washes cars, and then R sub C is going to be the rate Carl washes cars. Now it's a rate, and it's like I said earlier, it's going to have a unit divided by a unit. The rate in this case is cars per minute. It's the number of cars that you can wash in a certain number of minutes. So Bob can wash 1 car in 10 minutes. So his rate is 1 car per 10 minutes, or 1/10 of a car per minute. Carl can wash 1 car in 12 minutes. So his rate is 1 car per 12 minutes, or 1/12 of a car per minute. Now we use the same principle as distance is equal to rate times time. The distance in this case is not a physical length like feet or yards or anything. It's actually the number of cars that have been washed. So if you take the rate at which someone washes a car and the amount of time that they wash the car, that tells you how much of the car is washed. So I'm going to write this out too as well. So the number of cars Bob washes, that's equal to the rate at which Bob washes the car times time. And the number of cars Carl washes is equal to the rate at which Carl washes cars times time. And together, the total cars will be equal to the number of cars that Bob has washed, so that's R sub B times T, plus the number of cars that Carl has washed, R sub C times T. So let's form the equation and solve. So we're looking for how long it takes them to wash 3 cars. So 3 is equal to, and the rate that Bob washes cars is 1/10. multiply that by t, plus the rate that Carl washes cars, 1/12, also times t. We have an equation that has a fraction, so we'll find the LCD. The LCD of 10 and 12 is 60. It's actually the least common multiple of both 10 and 12. So I'm going to multiply both sides by 60. So 60 times 3, and then 60 times each of these pieces. 1/10 t plus 60 times 1/12 t. Let me come up here and finish the solution. So we have 180 is equal to 60 divided by 10 is 6t. 60 divided by 12 is 5t. Combine the like terms on the right. We get 11t. And then divide both sides by 11. And 180 divided by 11 is 16.4. This is time, so this is minutes. So if they work together, it'll take them 16.4 minutes to wash all 3 cars. Now, what if they didn't start working at the same time? Example part B here, how long will it take them to wash 3 cars if Bob starts 5 minutes before Carl joins, and then they work together to finish up the 3 cars? So we have most things set up, but the time is a little bit different. So we're going to use most of what we have before, but this time the number of cars Bob washes is still the rate that Bob washes cars, but the time is now t, the time that he and Carl work together, plus 5 minutes. The number of cars that Carl washes is the same as before. R sub c, the rate at which Carl washes cars, times t, the time at which they work together. So Bob is the only one that's working by himself, so he has more time to wash cars, and that's why you have t plus 5. We're still looking for how long it takes them to wash 3 cars, so it's 3 is equal to the rate at which Bob washes cars times t plus 5, so 1/10 times t plus 5, plus the rate at which Carl washes cars, 1/12, times t. The LCD, again, is 60, so we multiply both sides by 60. And clear those denominators. So we have 180. 60 divided by 10 is 6. And then 60 divided by 12 is 5. Distribute the 6 on the right side. So we get 180 is equal to 6t plus 30 plus 5t. Combine the t's on the right. So we get 180 is equal to 11t plus 30. Move the 30 to the left. Subtract that from 180 and get 150 is equal to 11t. I'll finish it on the right side here. T is equal to 150 divided by 11, which is 13.6 minutes. So it takes them together 13.6 minutes. So Carl worked the 13.6 minutes. Bob actually worked 18.6 minutes. In example 6, a car rental company charges $25 plus 5 cents per mile driven to rent a car. write the equation for C, the cost of driving X miles. So the $25 is a fixed cost. You're going to pay that regardless of how many miles you drive. So C is equal to 25 plus, and then it's 5 cents per mile. So we're writing C in dollars. So we have the 25, so we need to change the 5 cents to $0.05 times X for each mile that's driven. Part B, the car rental company charged Alejandra $33. How many miles did she drive? Well, the $33 must be equal to the cost that it cost to rent the car. So we'll set that equal to C here. So 33 is equal to 25 plus 0.05x. And then we'll solve for x. Move the 25 over. 33 minus 25 is 8. And then divide both sides by 0.05. And we get x is equal to 160. X represents the number of miles driven in the car rental, so that's 160 miles.